Hey, Ben and Kevin. All right, Thomas, more folks are showing up. That's awesome. Um, in just a second here, and we will get started. Today, we're going to begin talking about integral calculus. And the first formal lecture on this is actually going to be delivered by one of your peers. We have a next student teaching thing coming up. Let me come over here. But I'm pretty sure we're going to do that on Friday. So I had to think of what we're going to do today. Because the test kind of pushed things around. Yeah, 5.1 areas and distances. That's Kieran and Benjamin. So they are going to be delivering our lecture on Friday. I think that was the arrangement we made. One of you emailed me. I don't remember who. I think maybe it was Ben who emailed me. Making the arrangement. Or no, it was Katie. Katie and I talked, right? Yeah, the antiderivative lecture is the one that we're pushing. So today what I want to do is we've got kind of a filler day, basically. That's what I'm getting at, right? So because of the exam and spring break, things got bumped around a little bit, that's fine. But we have some topics that we need to cover that, that don't fit beautifully anywhere else. And you've technically seen before in pre-calculus, assuming you had a good pre-calculus class, but that are necessary for section 5.1. So let me just say this a little bit. Katie's lecture is going to be on Friday, and it's going to be on antiderivatives. Following that, Kieran and Ben are going to be lecturing on 5.1. What I'm going to do today is going to be a little intro to some of the things that you guys are going to need in section 5.1. So Katie, I think you're planning to talk to me today in the office hours and make sure everything is ready to rock and roll for Friday. Is that right? Are we still on track to do that? Awesome. And then, let's see. Oh, Ben Samuel is not here yet, right? And neither is Kieran. So hopefully those folks reach out to me soon and we can make a plan. Has anybody heard from them recently? Let's see. Oh, did we lose both of them? Okay. If that's the case, then I can take over section 5.1. That's fine. All right. Probably what we'll do then, yeah, I'll just take over it since it looks like I know Kieran dropped. I did not notice that our other Ben dropped. That's okay. I will take over that lecture from them. So then what we're going to do today is a little review of summation notation. So let's get into it. So in my non-honors class, we go through these things in a slightly different order. They covered 5.1 today because we don't actually use 4.9 until we get to the fundamental theorem of calculus. And I kind of don't want to scare them. Right, so today we're going to do a little intro section 5.1. We're going to talk about summation notation. And we might end up just straight up covering 5.1. That may end up being the way to do this because both Benjamin and Kieran have let go of the class. So let me turn on my screen share. We can get rocking and rolling. Okay, I get that out of the way. All righty. On Friday, Katie will teach us section 4.9 on antiderivatives. And the kind of miracle is that these concepts are connected in a deep way. 5.1 is on areas and distances. So it's kind of surprising that antiderivatives connect to that. But they do in a beautiful way. And the connection between them is what's called the fundamental theorem of calculus. Let's get to it. So section 5.1 is all about areas under curves. And distances turn out to be relevant here too. But the big focus is on areas under curves. Intuitively, what I'm doing here is I'm taking a function between two endpoints, say A and B. So I specify a function and I specify an interval. And I want to try and find the area in there. Right? This creates a little region, the area bounded by this curve and the x-axis. I want to try and find that. The question is, can we find the shaded area? And there's a couple answers to this. The first answer here is well, if the curve is nice and simple, right? Like if this happens to be like a linear function, then I could find that area just using geometry formulas, right? Like if this was a perfect rectangle, imagine that instead of a curvy thing here, I just had a straight horizontal line, then the area would just be a rectangle. And I can multiply the width times the height, and that would give me the area. But things get complicated when you have a curvy region like this. The first person to give a truly good answer to this question was Bernard Riemann, a mathematician from the late 19th century, early 20th century, mostly late 19th century. Although people before him gave reasonable attempts at answers also. Carl Friedrich Gauss famously invented what's called Gaussian quadrature, which is a method for approximating these areas, and in some cases getting them exactly right. And even before them, there were people working on this problem. One way to do this, we can estimate the area by filling up the space with rectangles. Right? Because I know how to calculate the area of a rectangle. You just take its length times its height, or its width times its height, and that will give you the area of a rectangle. So I can come in here and drop down a bunch of little rectangles, find the area of each of those rectangles, and say, okay, well, maybe it's not perfect, but it should be a reasonably good estimate for the area under the curve. And you can put the rectangles in like I just showed, vertically. And that leads to what's called Riemann integration. You can also put the rectangles in horizontally. And that leads to what's called Lebesgue integration. In this class, we learn Riemann integrals. So vertical rectangles. I'm just going to use a squiggly arrow here, leads to what's called Riemann integration. Horizontal rectangles lead to what's called Lebesgue integration. Integration, turns out, is just the math term for finding areas. It can be generalized to finding volumes, to finding surface areas, to finding all sorts of other cool things. but you'll hear me use the word integral and integration to refer to the area problem here that we're trying to solve. In this class, we will be doing vertical rectangles. These turn out to be a little bit hard. So if you want to learn the horizontal rectangle, the Lebesgue integral stuff, then you're going to need to go on to take some seriously heavy real analysis. I think it's usually introduced for the first time in like a second or third graduate course in real analysis. But the Riemann integral stuff is very manageable. So the vertical rectangle thing is what we're going to do. I don't want to overwhelm, but let me go ahead and draw the picture here. I'm going to redraw this nice and big, and we're going to take a stab at coming up with a formula. So let's try the vertical rectangle thing. All right. So if we're going to do this, try to find the area under f of x from A to B. Of course, first you need to be given a function, f of x, that you're trying to find the area under, and you need to be told what A and B are. The next thing you need to do is decide the number of rectangles. So your first step here is determine the number of rectangles. We call this n. The second thing we need to do is determine the width of the rectangles. And there's lots of ways we could do this, but the most natural thing to do is to make them all the same width, right? I could have some of the rectangles being really wide, I could have some of them being really skinny, and in certain settings, it makes sense to do that. But what we're going to do here is we're going to use all the same width, and that will make life easier. We call that width delta x. And remember, this delta means like a little change in. So it's like a little step in x. Since they're all going to be the same width, I have to, and there's going to be n of them, to fill up this space with n equal widths, you just take the total length, which is b minus a, and you divide by n. So we call that delta x. So if I was going to do that here, maybe it would look like this. I chop up that interval a to b into some number of equally spaced pieces. The third thing you need to do is calculate these endpoints. We call those endpoints xi. So this first one I would call x0. This one I would call x1. This one I would call x2. This one I would call x3. And I keep going. So as I've drawn it here, n is 8. The formula for these endpoints, if you think about it a little bit, you can come up with it on your own, I bet. Think about, how do I get to x4? How do I get here? Well, I start over here at A, and I walk 1 delta x, right? Because this width right here is delta x. 2 delta x, because this width is also delta x. 3 delta x, 4 delta x. So to get to x4, I start at A and I add 1, 2, 3, 4 copies of delta x. To get to x2, I would start at A and add 1, 2 copies of delta x. To get to x6, I start at A and I add 1, 2, 3, 4, 5, 6 copies of delta x. So in general, to get to xi, I have to start at A and add to that I copies of delta x. And at this point, you have a choice. Now, we choose whether the height of each rectangle will come from the left or the right endpoint. So what I mean by that, let me come in here and draw one of these for you. If I'm going to choose to have my height coming from the right endpoint, my first rectangle is going to be in here. And since I'm choosing to do from the right endpoint, it would look like this. I come out to the right endpoint of the first interval and I go up to my graph. So here would be my first rectangle. Now I look at my second little sub-interval here. To draw my second rectangle, I come to the second sub-interval, which is here. I look at the right endpoint and I go up to my graph. Like that. To choose the height of my third rectangle, I go to the third sub-interval, go to the right endpoint, and I go up to my graph. And we continue doing this. Go to the right endpoint, up to the graph. Go to the right endpoint, up to the graph. Go to the right endpoint, up to the graph. Go to the right endpoint, up to the graph. Go to the right endpoint, up to the graph. So each one of these rectangles touches the graph on its upper right endpoint, and that's why we call these the right endpoint rectangles. So here n is 8 and we use right endpoints. We could have used the left endpoints, and then my first rectangle would have started over here. My second rectangle would have started over here, my third rectangle like this, my fourth rectangle like this, fifth like this, and so on. We have to choose whether to use left or right endpoints, and we apply the formulas. So if I'm using n rectangles with right endpoints, what's the area of this first rectangle? What's its width? What is the width of that first rectangle? So the width isn't quite x1, it's the distance from A to x1. What is this distance down here? What's the width of any one of these subintervals? Remember when we were talking about these things here? Yeah, good, delta x, right? Delta x. Each one of these has width delta x, because we started by saying delta x is this total distance divided by n. So the width of each of these rectangles is delta x. What's the height of this first rectangle?
F of x1.
Yeah, good, right? The point right here is x1 comma f of x1. This point right here is x2 comma f of x2. This point right here is x3 comma f of x3. So these heights are coming from these y values. The last one over here is xn comma f of xn, or in this case, x8, I should say, comma f of x8. So yeah, so my first rectangle has area f of x1 times delta x, height times width. We're going to call this Rn. What's the height of my second rectangle? So I need to add to this the height of the second rectangle. That would be his height, which is f of x2 times his width, and his width is also delta x. This is why we like them to all be the same width, because it makes life a little bit easier here. Then I would have f of x3 times delta x, and we go all the way out to f of xn times delta x. So this is the area of the first rectangle. This is the area of the second. This is the area of the third, and you go all the way out to whatever n is, however many rectangles you have. So this is the area of the nth rectangle. As we drew it up here, n would be 8. But in general, n is just n. There's a nicer way to write this is actually, so I can factor that delta x out. And that would give me f of x1, because delta x is the same. The widths are always the same. So that gives me f of x1 plus f of x2 plus f of x3 plus all the way out to f of xn times delta x. So this is sort of your first important formula. And one of the things I'm going to show you guys today is how to write this using what's called the sigma summation notation. This is the sum from I equals 1 to n f of xi times delta x. So 3 kind of different ways of writing Rn, all equivalent. This is the right endpoint method. The term for this thing is called a Riemann sum. Named after Bernard Riemann, the guy who came up with the vertical rectangle attack. If, on the other hand, I wanted to use the rectangles coming from the left end points, not a whole lot changes. So I'll just give you the recipe here. Ln, the left endpoint Riemann sum. Instead of having my height of the first rectangle come from x1, it would come from x0. So that would be x0 times delta x plus f of x1 times delta x plus f of x2 times delta x. And this one's going to go not all the way to xn, but f of xn minus 1 times delta x. And again, you can factor out the delta x. So that would give you f of x0 plus f of x1 plus f of x2, all the way out to f of x n minus 1 times delta x. And this can also be written in summation notation as sigma I from 0 to n minus 1 f of xi times delta x. And this is called the left endpoint Riemann sum. So these are the two main formulas you're going to need for section 5.1. I would like to talk a little bit about just how to use it, just do an example or two. And then I want to show you how to get exact areas and how to work with these sigma notation things. So let's begin by doing an example. I'll give you a second to write if you need it. I feel sick in my nose. In all of these, you still need these three steps. You need to know what n is. You need to calculate delta x, and you need to calculate your xi's. These are always your first three steps. So make sure you have these near these in your notes. Okay. So an example. Let's estimate the area under f of x equals x squared from x equals 0 to x equals 1 using both Rn, I should say R4 and L4. So we're using the 4 rectangles. We're going to do the right endpoint and the left endpoint. It's always helpful to draw the picture. Here we're going to end up drawing 2 pictures total. I'm going to really exaggerate that distance there and mark that as 1. This is 1. So we know that x squared is like a parabola, and from 0 to 1, it looks like this. Of course, it comes over here and does more of the same. But I'm interested in what's going on from 0 to 1. So the region whose area I'm trying to find is x squared. All right, we're trying to find this area. Let's start by using the right endpoints. For both of these, I need to know what n is, and here's 4, because they told me to use 4 rectangles. For both of these, delta x. So what is a and what is b? Well, I'm going from x equals 0 to x equals 1. So a is 0 and b is 1. So this is always b minus a over n. That's 1 minus 0 over 4, which is 1/4. And then I need my xi's. The formula for xi is a plus I times delta x. So that's 0 plus I times 1/4, which is just I over 4. All right. So what that means is that x0 is 0, x1 is 1/4, x2 is 2/4 or 1/2, x3 is 3/4, and x4 is 4/4, which would just be 1. x0 is already plotted over here. That's always A. And x4 is over here. That's B. So then let's draw in the other ones. This is x1, which is 1/4, x2, which is 1/2, and x3, which is 3/4. So if I'm going to use the right endpoints first, my first subinterval is right here. The right endpoint of that is this. So I come up to my function and I draw my little rectangle. My second rectangle, I look at the second subinterval, which is right here. I go to the right endpoint up to my function and I draw my second little rectangle. Now I come to my third subinterval. Its right endpoint is here. So I come up here and I draw my third rectangle. And then I come to my fourth subinterval, which is right here. I come to its right endpoint, go up to my function, and draw my fourth little rectangle. So there it is. There are the rectangles that I'm going to use to estimate this area. You could just use the picture and try to figure out the area of each of these, but it's important that you're also comfortable using that formula. So R4 is, I'm going to use that second form of the formula, f of x1 plus f of x2 plus, I need to go all the way out to x4 here. So f of x3 plus f of x4 times delta x. That is R4. Each one of the little things here are heights. And the thing out here is the width. Since all the widths were the same, we could factor it out. Remember, that's what we did here. So this is really like first height times the width, plus the second height times the width, plus the third height times the width, plus the fourth height times the width. So these are areas. If you were to distribute this delta x through, f of x1 times delta x would be the area of the first rectangle, right? That's f of x1, that's this height, times delta x, that's this width. Second one would be f of x2, that's this height, times delta x. F of x3, that's this height, times delta x, and so on. So x1 is 1/4. x2 is 1/2, x3 is 3/4, x4 is 1. So I'm going to just plug those in now. This is f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1, all times delta x, which was 1/4. What is f of 1/4? What's the function f of x here?
X squared.
F of x is x squared, good. So what is f of 1/4?
1/16.
Good, yeah, I'm gonna even take the intermediate step of writing it as 1/4 squared. F of 1/2 would be 1/2 squared. F of 3/4 would be 3/4 squared. F of 1 is 1 squared. And then I've still got my 1/4 out here. If the function I was messing with was cosine, then this would be the cosine of 1/4, the cosine of 1/2, the cosine of 3/4, and the cosine of 1. But the function I'm messing with is x squared. So f of some stuff is just that stuff squared. Now all we have to do is clean this up, right? We just have to figure out what this number is. So what is this number? Well, 1/4 squared, like you said, is 1/16. 1/2 squared is 1/4. 3/4 squared is 9/16, and 1 squared is still just 1. And this is all being multiplied by 1/4. And then I can have a common denominator and sort of clean this up. This is 1/16 plus 4/16 plus 9/16 plus 16/16, all times 1/4. So what is that? That's 5 plus 9 is 14 plus 16 is 30. So that's 30/16 times 1/4. And if you try to clean this up, 30 is divisible by 2, that's 15. You have to have a 1/2 down here. So this is 15 over 32. So the area under my curve is somewhere kind of close to 15 over 32. Is this an overestimate or an underestimate? Is this too big or too small? Yeah, good. This is a significant overestimate, right? Because this rectangle, look how much of that pokes out past my curve. All of this shit is an overestimate, right? All of this stuff shouldn't be counted. I'm trying to find the shaded area, the gray area. So these rectangles are too big. This is a significant overestimate. Overestimate probably should be hyphenated. Overestimate. Questions about how we came up with 15 over 32? How we knew to start with this formula, any of this stuff, or any of this stuff? Okay, then let's go ahead and calculate L4. Same function and everything. I'm going to redraw my graph. You should always, always, always draw the picture on these drawings. Again, I'll exaggerate the distances a little bit. So call that 1, call this 1. Of course, this is 0. And I'm interested just in 0 to 1. So the area I'm trying to calculate is this shaded area here. And I'm doing the same thing. So here n is still 4. Delta x is still 1 minus 0 over 4, which is 1/4. And so my xi's are still a plus I delta x, which is going to be I over 4 still. So x0 is still 0, x1 is still 1/4, x2 is still 2/4 or 1/2, x3 is still 3/4, and x4 is still 4/4 or 1. And come in here and try to draw these. The difference this time is that I'm using left endpoints. Right, so f of x still x squared here. But this time I want to use my left endpoints to determine the height. So if I come in here and look at this first subinterval from 0 to 1/4, the left endpoint there is right here. So the height of this first rectangle is actually going to be 0. All right, we can kind of try to draw it in here and just make this more bold. And then if I look at my second subinterval, the left endpoint is here. So we go up to my function and we draw a rectangle. My next subinterval is 1/2 to 3/4. The left endpoint there is 1/2. So I go up to my function and I draw my rectangle. And then my last guy here is right here. So here's the picture for left endpoints. Same function, same interval, 0 to 1, just left endpoints versus right endpoints. L4, if I take the formula for Ln and I plug in 4 for n, this would be f of x0 plus f of x1 plus f of x2 plus f of x3 all times delta x. Now I plug in. X0 is 0, so this is f of 0 plus f of 1/4 plus f of 1/2 plus f of 3/4 all times delta x. F of 0 is 0, or 0 squared. F of 1/4 is 1/4 squared. F of 1/2 is 1/2 squared, and f of 3/4 is 3/4 squared. And my delta x, sorry, I should have put it in at the step. Delta x is 1/4. Yeah, let me go back and this is a 1/4. Nice to put that in that step. So 0 squared is 0. That's 0 plus 1/16 plus 1/4 plus 9/16 all times 1/4, which is 1/16 plus 4/16 plus 9/16 is 14/16 times 1/4, which is going to be yeah, 7. So you can cancel the 2 here and you get 7/32. And this, based on the picture, is an underestimate, right? The area of the rectangles is less than the shaded area because there's all this stuff which isn't being counted. This is a significant underestimate. What could I do? And so I'm going to want some ideas from you guys here. What could I do to improve these estimates?
Set n to like a bigger number, so you have more rectangles.
Yeah, more rectangles is a great idea. So I could use more rectangles. I could use a bigger value for n, right? What else could I do? So Julio's suggestion there is a good suggestion, and it turns out that's the one we're going to use when we want to get the exact area. We're gonna use a shitload of rectangles, but there are other things too. I'd like to hear what you guys have to say. Are there any other ideas what we could do? Think about the fact that one of these is an overestimate and one of them is an underestimate, right? If you know one is too big, yeah, Kevin's idea there. What if we used like triangles? So these, it turns out, Kevin, I think what you're saying here isn't exactly what I'm thinking. These shapes in here are not actually triangles, right? Because if you zoom in, if you zoom way in, you'll realize that they're curvy. So here's a good first thought. But if you look at this little region here, for example, you see that this line is not actually a line, it's curved. This line is not actually a straight line, it's curved. This looks like a straight line, but it's really not. It's slightly curved. These are all curved. So they're not triangles. But there is something else I could do. What if we average Rn, which was too small, or sorry, which was too large, with Ln, which was too small? It turns out there's a name for this. We call it Tn, and that's the average 1/2 of Ln plus Rn. And this gives you the area that you would find if you had what are called trapezoids instead of rectangles. So Tn here stands for the trapezoid. Trapezoidal Riemann sum. It's called that because if you, instead of using rectangles, used trapezoids, like I draw the straight line connecting any two of these, that would give me this thing. So here, 1/2 of L4 plus R4 would be 1/2 of 7 30-seconds plus 15 30-seconds, which is 1/2 of 17 plus 15 is 22 30-seconds, which is 11, 30 seconds, 32, which is 11 over 32. And this turns out to be really close. So the geometry of what's going on here with Tn, let me show you. I'll hold here for a second. This Tn thing, it's useful. We're not going to use it a lot in this class, but you'll see it discussed in Calc 2 when you talk about estimates for integrals there. Is a cool thing I want to show you here. So a trapezoidal Riemann sum, here, look at this. Instead of using the left or the right endpoints, you kind of use both. And you make this little trapezoid. That's the name for a parallelogram where one side is longer than, it's not a parallelogram, but it's the name for a shape like this, a rhombus, where the one side is longer than the other. You got two parallel sides and two non-parallel sides. So that would give you actually a really good estimate. But it's not something that we discuss a lot in this class. But I wanted to just say that because we know that this is an overestimate, you know that this is an underestimate. So the average of the two should be a little bit closer to the actual area than either of them on their own. And in this case, 11 over 32 turns out to be real fucking close. Like it's off from the actual area by 1/32. But what I really want to talk about is option 1. Option 1 is how we get the exact area. Specifically, what we're going to do is send the number of rectangles n to infinity. So as I use more and more and more rectangles, my estimate gets better and better and better and better. There are some pictures in the textbook that help you see why this is the case, and I would like to show you those pictures now. Here we go. So here's the left Riemann sum, the left endpoint Riemann sum for x squared from 0 to 1. Here they're using slightly more rectangles. Here's 8 rectangles. It's getting a little better. Here we're using more and more and more rectangles. And if you look at this picture here, you can tell that as we increase n, here's n equals 30. This is looking pretty good. N equals 50. This looks like it's almost exact, right? Look at how close this is. The actual area under the curve compared to the rectangles here, because the rectangles are getting so small in width, the little bits that poke out above the curve are getting smaller and smaller. And you see the same thing happening with Ln too. As n gets bigger and bigger, the area of the rectangles is getting real fucking close to the area under the curve. So we use more rectangles. How many more? Well, you could use 10 or 20 or 50 or 1,000. If you want to get the exact area, you send n to infinity. So here we go. Fact. The exact area under f of x from x equals a to x equals b is given by the limit as n goes to infinity of Rn. And it turns out that that's going to be the same as what you would get if you look at the limit as n goes to infinity of Ln. But we'll use Rn. Just because it's usually a little easier to calculate with. And the limit, so let's return to f of x equals x squared from x equals 0 to x equals 1. I want to find the exact area. Well, I know that Rn is f of x1 plus f of x2 plus all the way out to f of xn times delta x. Here, n is just n. I'm sending n to infinity. We treat it as a variable. So the big difference here is when you're going to find the exact area, you're not plugging in a specific number for n. You just leave it as n. And that has an effect on everything else. That means delta x, which is always b minus a over n, would be 1 minus 0 over n, which is just 1 over n. This also has an effect on our xi's. Xi is still and always a plus I delta x. And a is still 0, but delta x is now 1 over n. So this is just going to be I over n. So if you think about this, this means, let's come back to our Riemann sum. If I write it in that sigma summation notation, this is the sum from I equals 1 to n, f of xi times delta x. So all of these things are over here. Now what I want to do is take the limit as n goes to infinity here. I can plug some things in. This is sigma I from 1 to n, f of xi, well, xi is I over n, times delta x. Well, delta x is 1 over n. And what is f of I over n? Well, since f of x is x squared, that piece, everything else staying the same, that piece is I over n squared. And then I still have my 1 over n here. I'm going to go ahead and run through this in the sigma summation notation. And then we're going to go back and talk a little bit more about this sigma notation. at one step in this process, I'm going to use a formula that you may or may not remember from pre-calculus, and I'll go back and show you what those formulas are. Make sure you have everything you need. But first, I just want to solve this problem. I want to find the exact area under x squared from 0 to 1. So the exact area is the limit as n goes to infinity of Rn, which is the limit as n goes to infinity of the sum from I equals 1 to n, I over n all squared times 1 over n. Now I'm going to do some algebra. This is the limit as n goes to infinity of sigma I from 1 to n, I squared over n squared times 1 over n. So I'm just taking this I over n squared and squaring the top and bottom. That's how you square a fraction. Next, I squared over n squared times 1 over n is I squared over n cubed. Next, this is sigma I from 1 to n, 1 over n cubed times I squared. And since this 1 over n cubed doesn't have any i's in it, it can come outside the sigma. So I get limit n to infinity 1 over n cubed times sigma I from 1 to n of I squared. And there is a summation formula from pre-calculus sigma I from 1 to n of I squared, that's n times n plus 1 times 2n plus 1 all over 6. So this piece becomes lim n to infinity 1 over n cubed times n plus 1 times 2n plus 1 all over 6. And like I said, don't panic. Just make sure you're getting this clearly and cleanly in your notes. I know it's likely that you do not have a lot of experience with this sigma symbol. So after we run through this, I'm going to go through and give you a kind of introduction to and little practice with this sigma symbol. This is now something that we learned how to do back in section 2.6. Downstairs, I have 6n cubed, right? 1 over n cubed times stuff over 6. Upstairs, I can start distributing. I'll do it over here. N times n plus 1 times 2n plus 1. That's equal to n squared plus n times 2n plus 1, which is 2n cubed plus 2n squared plus n squared, plus n squared plus n. Oh, damn. So this up here is 2n cubed plus 3n squared plus n. And if you renormalize, this is a limit as n goes to infinity. The top and bottom are both going to infinity here. So you could use L'Hopital's rule also if you wanted. But it would take 3 applications of L'Hopital's rule. And this is a simpler problem here. This is one that we learned how to solve back in 2.6. You can renormalize, dividing top and bottom by n cubed. We get 2 plus 3 times 1 over n plus 1 over n squared, all divided by 6. So as n goes to infinity, 1 over n goes to 0. 1 over n squared goes to 0. You get 2 plus 3 times 0 plus 0 all over 6, which is 2 over 6, or 1/3. So the exact area under x squared from x equals 0 to x equals 1 is 1/3. And this is how we figure this shit out. All right, again, I fully acknowledge that this is a little bit scary looking. So for right now, for this exact moment, I just want you to make sure you have this nice and clear in your notes. You have everything written down correctly. I will explain this summation formula along with a few others that you're going to need to use, and how to use the sigma operator in general. I'm going to hold here for a few minutes in case anybody is writing. Are there any particular steps here that we want to talk about? Okay. I'm moving on in about 10 seconds, unless somebody asks me to hold somewhere or something. All right, moving on. So 1/3 was the exact area. If you look under x squared from 0 to 1, even though that's a curvy region, we can find that exact area. That's really exciting. This is a hard problem to solve. And you can see why it would take so long for mathematicians to figure it out. The Greeks wanted to do this. Some folks in ancient India wanted to do this, but we didn't have a good, solid, reliable way to do it until Riemann. So literally thousands of years of people working to figure this stuff out. There's 2 kinds of problems. That you need to know how to solve in 5.1. Estimating the area. And this is where an n value is given. Like n equals 4 or n equals 10. Here, you're going to use the formulas for Rn or Ln as called for, and just do the calculation. By finding n
delta x, the xi's. And just you plug in and you go, you know. Always worthwhile to draw the picture. This is your first kind of problem. The second kind of problem here is finding the exact area. Here, n is treated as a variable. And we, again, use the formulas. Formula, really, we just use for Rn. Then evaluate the limit as n goes to infinity of Rn. This is where the sigma notation is useful. So if n is 4 or 10 or something like that, then you can just write out Rn. But if n is a variable, if it's just being treated as a variable, then you know there's no nice way to write out Rn. Let me remind you what those formulas look like. The two formulas in question for Ln and for Rn. Here's the formula for Rn. Right? If you have a particular number for n, then this is the version you want to use. Because like, you know, maybe n is 5. Okay, f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 times delta x. You can actually write it out. It's got a defined length. But if you don't have a specific number for n, then you need to be able to treat n as a variable, meaning your length here is a variable, which means it's very hard to write this out in a way that makes it usable. That's where this version comes in. These say the exact same thing. This piece right here is this piece right here. So what I want to do is talk about the sigma operator and make sure that you're a little bit comfy with that. There are some other things in section 5.1 that I want to talk about also, like some physics problems where you're going to find the distance that a particle travels, that sort of shit. There are some issues with signs, like being above the x-axis versus being below the x-axis and what that does to our area calculations. It turns out this measures a signed area. So area beneath the x-axis is counted as negative. But all of those things I'm going to push down the road a little bit so that we can try to get you kind of comfy with sigma summation notation. I'm going to check the time here to make sure I've got a little bit of time left to play with this. Oh, fuck, I don't. All right, so next time, let me see where we're at. Katie is going to come talk to me today. Let me see. I may end up, yeah, so I won't. Next time, I think what we may end up doing, and this, I hope you're okay with this, Katie, especially since we lost Sam and Kieran. Yes, sure. There are two kinds of problems. So I think next time, probably what I'll do is I'll continue the 5.1 lecture. Katie, you and I should still meet today in office hours to talk a little bit. And then maybe I'll ask you to push the antiderivative lecture even to next Monday. That way we can keep the 5.1 stuff together. And then the antiderivative lecture goes very nicely with section 5.2. So I'll lecture a little bit more on 5.1 on Friday. And then I'll ask you to do your antiderivative lecture next Monday, if that's okay with you. All right, we're pushing things a little bit around, a little bit out of order, but it works, and I think it will actually work better this way. But still, please come by my office hours so we can take a look at what you've got so far and make sure everything is ready to rock and roll. Is there anything else that you guys need from me right now? Everybody have time to get this down? Alrighty then, I'll go ahead and end the lecture here. On Friday, we're going to talk more about section 5.1. And then on Monday of next week, Katie is going to teach us all about antiderivatives. And then we'll follow that up with the connection between the two. So it turns out that finding areas like this is intimately connected to finding antiderivatives. But again, it's a little bit complicated, and we're going to need to take some time to get there. So I hope you guys have a lovely rest of your day. I'm going to drop a new homework here in just the next few minutes. Please take a look at that homework and work the first few problems. The first few problems will be problems like this, where n is given, right? I say, use 5 rectangles, use 7 rectangles, that sort of shit. The next few problems in that homework set will be like this, where you have to find the exact area by calculating the limit as n goes to infinity of Rn. You can take a look at some of those between now and Friday if you want, but I will lecture more on how to solve these on Friday. Alrighty, gang, that is it from me. I hope you have a lovely rest of your day. If you want to see me in office hours, they're 1 to 2 today, and that is it. Take care.